In this video, I'll talk about electric field due to a line charge. So we have a line charge. It's a very long line charge. It's infinitely long. It extends from negative infinity to positive infinity. That's how long it is. It's a very long line charge. And here, and it is uniform in the charge is uniformly distributed. We assume the line charge density for this infinitely long wire is lambda. That means the charge per unit length, on unit length, the amount of charge is lambda. So we are interested in finding out the electric field at any point. Let me draw this way. So we are interested to find out at a point which is at a distance y from the wire or due to the charge. So this point P is at a distance. So this point P is at a y distance from the wire. And at the point P, we are interested in finding out the total electric field. How are we going to solve it? In order to solve this one, what we're going to do, we're going to assume a very tiny charge onto the wire. So let's do this way. Yeah. So here we have assumed a very tiny charge dq. Oops. The tiny charge dq, and the length of this one is dx. This is the length. And again, what we're going to do is, let me draw the other color. Now we're going to do the tiny segment here, the d, which has the charge dq, and the length is dx. And this distance, this is, let's say this is our origin O, this is our x-axis, and this is our y-axis. And this distance is x, and this is also x. Both the distance are x. Let's call this angle theta. So this angle will also be theta. Now let's find out the direction, as this is a positive charge. This is positive charge, all right? And we remember the electric field due to a positive charge is away from the charge. So if we take the tiny positive charge here, and at this point, the electric field due to this tiny charge will be away. So this will be the direction. So the direction of is given in this direction. Now, if we take this tiny charge here, dq, then the electric field due to this tiny charge at this point is away again. So the direction in this case will be along this direction. Okay. So we have the electric field in two different directions due to the two tiny charges. So how are we going to solve this problem now? In order to solve this problem, we're first going to resolve the electric field into two components. Let's first resolve this electric field into two components. We first call this one dE, because this electric field is coming due to only a tiny segment. That's the reason we call dE. And the same thing, we call this electric field again the dE. The magnitude is same because both the charges are dq, all right, and are at the same the distance. And this distance is r is equal to let me write down here. This distance is r is equal to x square plus y square. The same way, this distance is equal to r is equal to x square plus y square. Okay, so now let's first resolve this into two components. All right, so one component, this component here, as this angle is theta, this angle is also theta. So this component will be dE cosine theta. And the vertical component or the y component, this component will be dE sine theta. Okay, so we have resolved this electric field now. Let's do the same thing for this electric field now. We are again going to resolve it into two components. The one component will be along the x-axis, and this one at this angle is theta, or this angle is theta, this angle will again be theta. So this component will be dE cosine theta. Okay, and this component here will be dE sine theta. Okay, so now, so we have the two x component, dE cosine theta this way and dE cosine theta this way, and these two are equal in magnitude. So this component cancels out this component, and along the y-axis these two components add up together. Okay, so the total electric field is only along the y direction. Okay, just remember, because the horizontal component, this horizontal component cancels out, these two cancels out, and along the y-axis they have the same direction, so they add up together. So the total electric field is only along the y direction. Okay, so this total field, let me write down here, the total electric field can be given by minus infinity to infinity, and it has only the y component here. And this, what does this dEy means? This dEy, this means the electric field at point P due to one of the charges. Okay, again, this dEy means the total electric field at point P due to this charge. Okay, so now let's first find out what is dE. What is the electric field at this point due to this charge? Okay, electric field at this point due to this charge. We'll just write down here, the dE at this point is given by K, and what is this charge here? dQ. This charge is dQ. And what is the distance? The distance from this point, this distance is r. So remember, this is r square. And also, if you look into this triangle, the sine theta from this triangle is given by the sine theta, it will be y over r, which is given by x square plus y square. Okay, and also I'm just making all the notes here. So the dQ, how much is the charge? How much is the charge onto this tiny charge here? The dQ can be given by lambda times dx. Why lambda times dx? Because the lambda is the charge per unit length. How much you have charge in a unit length. So if you multiply by the length, then this will give you the total charge onto this tiny length, which is dx. Okay. And the one last note, I think we already have made it. R is equal to x squared plus y squared. This is the square root. Okay. With this one now, we should be able to derive the electric field due to a line charge. There are various ways of doing this one. Ey. And now let's minus infinity to infinity, and dy, the electric field at this point P, due to this charge, has the only y component, because the x component cancels out, so we have only y component, and the y component is given by dE sine theta. All right. And remember, if we take 2e, if we just take 2e d sine theta, then we have to integrate from 0 to infinity. But here I'm just taking one component dE sine theta, then I'm integrating from negative infinity to positive infinity. But if you just take 2e dE sine theta 2, then you have to integrate from 0 to infinity. Now, okay, let's solve it further. Ey minus infinity to plus infinity, and you see this dE value is given right here. This is the dE value. So what is it? K dq over r square. And sine theta, this sine theta is also given here, and the value is y over x squared plus y squared. Okay, so now let's solve it. Ey minus infinity to infinity k dq y, and also let me write down this way. dq, this dq here is given by lambda times dx. So what I can write down, k, instead of dq, I'm going to write down lambda times dx. All right. So this one will be lambda times dx. And then you have y, and again r square. R is given by x squared plus y squared. If you square, it will be simply equal to x squared plus y squared. And then you have this term here, x squared plus y squared. Okay. Now, I'm just trying to simplify things. So let's put all the constant at one side. K is constant, lambda is constant, y in this case is constant. Because y is constant because the y is the distance from the origin to this point, so y is constant. So all the constant term we're just keeping at one side. K lambda y, and then we have dx over x squared y squared plus this term together. This is power half and this is power 1, so it will be x squared plus y squared power 3/2. Okay. And now we can further simplify this one. This is now a symmetric equations. It's an even function. In even function in x, because this is x squared, so it is an even function in x. So for those who have taken the calculus class, so as this is an even function, I can simply write down, and this is a constant. So I'm just taking that constant out, k lambda y, and minus infinity to infinity dx over x square plus y square 3/2. And further, k lambda y, as I said, this is an even function, so I can write down from 0 to infinity dx over x square plus y square 3/2. And 2k lambda y, the integration of this entire term you can find out in any book, and this one is x over y square over x square plus y square, and the limit is from 0 to infinity. Okay, so now 2k lambda y, and now what you have to do, x, and this is y squared, so I'm taking it out, and I can take x out from this equation. So if I do that, then what I will get is 1 plus y over x square, and again 0 to infinity. This x and this x cancels out, so you have 2k lambda over y, 1y is cancels out here. Okay, so what I'm left with is 1 over 1 plus y over x square from 0 to infinity. And now let's plug in all the values now. 2k lambda over y, if I plug in infinity, what will I get? What I will get is, if I plug in infinity, then it will be simply equal to, no, instead of x, you'll get 1 plus y over infinity, which will be 0, minus 1 over 1 plus y over 0 square. Okay, so this is 2k lambda over y, and this term will be 1 over 1 plus y over infinity, so this is equal to 1 plus 0, minus this will be 1 over 1 plus y over 0 is infinity, so this is infinity, so this term will be 0, and this term will be 1. So what we left with finally is the total electric field. So the total electric field now can be given by 2k lambda over y. This is the total electric field due to a line charge. Okay, and what you see here, the thing you have to notice here, the electric field varies as 1 over y. If you, so electric field varies as 1 over y. So if you have to compare a point charge and a line charge, the point charge to the electric field due to a point charge varies more rapidly than compared to a electric field by a line charge. Okay, so this is the equation for the electric field due to an infinitely long line